All right, morning. So today is Thursday, April 5th, and today we're going to continue our discussion of generalizing recursion both at the function level and at the type level. So let's take a look first at this example here about the factorial. So we had gone through this, and we looked at basically different styles of, well, we went through a similar example for reversing lists. So here we're looking at factorial, and we're looking at a straightforward recursive definition up there. And let's see first, so the one on line 5. So it says this is a function from int to int. It takes an argument n, which would have to have the argument type given in the type signature, so int. And in that case, the function computes this conditional expression. So if n is less than or equal to 0, then return 1, else return n times the factorial of n minus 1, so applying this recursively to itself. So first of all, is this tail recursive, this implementation?
No, it's not.
Okay, why not?
Because the last operation is the multiplication.
That's right. So the recursive call happens before the last step, which would be the multiplication. That's exactly right. Does everybody see that? So that could be an issue, so that's why we'll look at a possible tail recursive implementation, which would be this one here, which uses the accumulator. So this corresponds more, as we saw in the list reversal, to a translation of a while loop-based implementation to a recursive function, right? So this would be just like starting n at the number whose factorial we want to compute, and then counting down n until it reaches 0, and with each iteration multiplying the current value of n into the accumulator, right? So these accumulator-based implementations are, in that sense, very, very similar, or can be considered a pure, non-mutable, non-imperative version of the corresponding familiar implementations based on a while loop, right? And now, is this one tail recursive? Yes, because the very last outermost thing here is the recursive call. And in fact, if you use the Scala tail recursive annotation, so Scala annotation tailrec, in that case, as we discussed, the compiler will verify that the function is tail recursive and will perform the optimization. It will basically avoid a call followed immediately by a jump back or by a return, and which is a jump back to the original caller. So it will effectively convert this code into a while loop or some kind of loop-based code. Down in the bytecode, it's more based on jumps. Okay, so, and here you have to start with some initial value for the accumulator. You can make that an optional argument, but let's say you start with the accumulator as 1, and then it'll work as intended, right? And this is equivalent, and the only difference is it uses an explicit case distinction based on pattern matching, which makes it look a little more like the mathematical definition, perhaps, but otherwise it's equivalent to this if-else-based implementation. And it's also tail recursive because in the non-base case, the very last step is making the recursive call. So far, so good. So we understand recursion, and the question is, so just like we looked at the ability to implement, and let's actually go back to that for a second here, and then cycle back to the part that we're about to discuss. So let's look at functions on lists for a second. So this is what we looked at. So here's reverse. And we saw, okay, so we can efficiently implement reverse as a fold left. Okay. And fold left itself, when you look under the hood, and these links here in section 4.4 are meant to go directly to the implementation code. Okay, so here's your fold left, and surprise, surprise, what do you see here under the hood? So this is for an immutable list, right? What do you see here under the hood? There's some imperative stuff going on, right? So, in other words, the fold left, you could implement the fold left naturally in a tail recursive way, but the implementers of this library, so Adrian Morse most likely wrote this code, he said, well, why not just do it ourselves, go all the way and just write it under the hood as a while loop in such a way that the imperative stuff that happens under the hood doesn't leak out. So when you're using the fold left method on this list, the fact that there's mutable stuff with a bar, with two bars going on here, that's completely hidden from you as the user. So this is considered acceptable because it's really just something that the library implementer decided to do for performance reasons. In this case, of course, space complexity, right? To make sure that we have constant space in the form of these variables. So what's going on here? Well, we start the accumulator, which is for building up this successive result of the fold. We start that with the initial value z, and then we start the iteration over the underlying collection with the current collection, this, and then we say, well, as long as we haven't reached the end, we'll apply the operation to combine the current accumulated result and the current item, and then we move to the next node. So you see how this is equivalent to the kinds of node-based iterations you would have written in, let's say, 271, right, where you start with the head node, and then you keep moving to the next node until you reach the end. So it's exactly that type of code here, right? So we got our fold left, and the fold left, any questions about this fold left implementation? And another thing you might find interesting is, of course, if you look at the implementation of reverse, so this reverse is also based on a while loop, okay, just to kind of manually optimize based on a while loop. So this just says, as I iterate the items I find, I build up a new list in the opposite order. Like prepending the items, as I go through the original list, and I get the resulting list in reverse order, and it's all very efficient, constant space. Linear time, obviously, because we got a linear number of items, and constant space. And now, so these are not surprising, although you might find it a little surprising to see this imperative code with mutable vars under the hood. But now the funny thing is, if you look at fold right, because we discussed that a direct implementation of fold right would be non-tail recursive and would require linear space, right? Therefore, the more efficient implementation of fold right, even though it looks like you're doing twice the work, but that's only a constant factor in time. So to do the fold right, you say, well, reverse, and then do the fold left on, you know, the operator with the argument switch. That's what this is for. So right and left are switched here. Okay, but it's basically reverse first, and then do the efficient fold left, and this means time complexity goes up by a factor 2. Okay, so which means it's still order n, right? By factor 2, you have, if you have order n and you bring in a factor of 2, you still have order n, right? But what about space complexity? Fold right, a normal implementation of fold right would be order n space because it's not tail recursive. And by using this reverse and the order 1 space while loop based fold left that you see here at the top, now space complexity of this step is order 1, right? And space complexity of this step also order 1. So in other words, you made a small sacrifice of going from order n to slightly more or slightly bigger order n by this factor 2, because you're doing 1 order n time-wise step, the reversal, and then you're carrying out the fold left, which is also order n time complexity. But you're staying at the same order of magnitude in terms of time, but space you're cutting down from order n to order 1. So by a whole order of magnitude going from linear, or order of complexity here, going from linear to constant. So that's a much, much more favorable trade-off. Does everybody realize that? So, and these while loops are very efficient. So that's why we have this clever implementation of fold right under the hood. Okay. So that's something I just wanted to kind of cycle back to. Any comments, questions? Now let's look at these separations of behavioral concern. So what we know, of course, is that fold left is like a Swiss Army knife almost. It enables us to implement many behaviors that would otherwise be based on some kind of loop over the entire collection. You know, so examples are finding the maximum, summing up the items, those kinds of things, right? And or even, as we saw, doing the reverse, right? So reverse can be based on fold left if we implement it ourselves, but because so the reverse that we find under the hood is really just a specialized implementation of fold left, because it's a common operation to say, well, let's just basically inline the step of creating the new node with the new item we're prepending to the list we're building. So it's like just a specialization of the code of the fold left. Okay. So even map, of course, can be a fold left, and in fact we should look at, let's say, do I have a map here? Yes. So let's take a look at the map also. What does the map implementation look like? So even the map is more complex, seemingly, because the Scala library has this complexity in its implementation that has to do with the specific representation. So it's basically designed for aggressive code reuse. So extremely DRY, do not repeat yourself. And that's why it has this BF, which is built from, so it's for managing the actual representation underneath the abstraction. So that's why this looks a little more complicated. But the key thing is it basically iterates through the list, and whenever it looks at another node, it applies the function f to the head, and then adds that resulting value, that transformed value, to the new list it's building. The part that's complicated is building the list using basically this this BF and looking at the BF. But the essence is really just iterating over it. So if you knew that it's a linked list based on these double colon nodes. Remember that the double colon that's just a symbolic name for a node case class. Like your nodes in a linked list with a head and with a value and the next. So head and tail, that's the same thing. Okay, so the key thing is we're just adding a node where the data value is f applied to the data value in the corresponding original node, and then we're setting let's see, right, so we're then advancing to the next node. So we're saying, okay, T is your current node. So we're saying, okay, T's tail is an X, and then we're moving T to the next node. So we're linking this node into the list we're building. Okay, but we could have written this as a fold left also, right? So let's see if we have that here. Well, let's do that here. So little live exploration here. So by implementing map as fold, you can also appreciate the generality of fold in terms of the result type, right? So it could produce a scalar type like int, for things like computing the length or so, but it is also capable of creating results of some collection type or the type of the underlying list itself. And the power of the fold is in its ability to basically represent or capture the commonality among actual behaviors such as sum, max, map, all of those. So the commonality is iterating over each item and then doing something with each item by kind of maybe a combination of applying some method that takes this item and then computes or adds this item to a combined result, right? So the fold allows you to capture that general common recursion pattern, and you just kind of plug in an argument that is a function that represents what is different, for example, between a sum and a max, right? So that's what the fold gives you, the value the fold adds. So let's see. Okay, here we are. Okay, so if we say list 2, 3, 5, right, and we say res 0 fold left, and then we can say start with 0 and then add the arguments, right? So there we get the equivalent of sum, right? So here's your sum. And let's try the map, so map as fold, and then the item type T, and then let's say, okay, because this is not a method, we have to have an explicit argument for our list X's. So list of T, and then what should this produce? Well, what do we need first? So we need, of course, also a resulting item type U, right? Because map, what does it do? Well, it takes a collection or a list of some item type T, and then it creates something that has exactly the same structure, the same kind of physical structure, but each item in the new structure corresponding to the old structure is just F applied to the old item, right? So I'm deliberately expressing this in a very general way. So what do we need? We need the function F, right, that we want to apply to each item in the original list of T. What is the type of F? Well, it takes an item of type T and produces an item of type U, right? That's why, that's the transformation. So, for example, if we have a list of strings, let's just take a look at map, an example of map. So, list, hello, what up, map, and then we can say S mapped to S dot length, or we could just say underscore length, right? What do we get? So so here T is string and U is int, right? So this is an example of map. But the structure is exactly the same, right? So let's see, make this a little bigger perhaps. Okay. So the skeletal list structure is the same, but only the items in the different positions have been transformed. Okay. So let's look at the map as fold, or map as fold left to be precise. What exactly do we do? So we say, first of all, what do we get as the result? A list of type U, right? Because each item of type T in the original list gets transformed by applying F to it. So we get another value of type U. It's a little small. Let's try again here. Okay. Here we go. All right. So how do we define it? Well, let's try this. So X is fold left. What do we start out with? Well, got to start out with an initial value that would be the right result if our collection X's were empty, right? So we've got to start, well, so 0 is too specific. Also, 0 doesn't have the right structure. We're going to have something that is, so map is structure preserving, right? So it takes a list and it produces a list. And the only list that would work regardless of the item type as the initial value is the empty list. So we'll have to say something like empty list of type T. Does that make sense? So if X's is empty, we get this empty list, and that's the right result. The only problem is it's got to be of type U, because that's our result type, right? Now, we have to say, what do we do? So our resulting list is R, and each item is X, because the list is X's. So each one is an X. So what do we do with R and X? So assuming R is the list of type U we've already built up, so we'd have to say, well, let's take R, and then we'll have to append what? Well, X itself we cannot append because that has type T. So how do we get a value of type U from X? How do we convert the current X of, yes? Applying F, because that's really the essence of map. So let's try that. So what we're building up is, we're going through the list, and we're successively building up by adding F applied to the X values we encounter. Okay, so let's see if this works equally well. So let's say we have list of hello world, what up? Same list, okay. And now our method, same thing. Our F would be S dot length. Let's see if this works. And it works exactly the same way. Okay. Any concerns though about this particular implementation? And that's tied to the fact that when we looked under the hood of the actual map, we found a while loop. What is the drawback of this implementation of fold left? It's tied to something we had on our recent quiz. Is this font big enough? Can you read it from the back? Can you read this? Okay. Yeah, just whenever you cannot read something, let me know immediately. Okay. Any concerns about that second line up there? The actual implementation of the map as fold left. So particularly, we'll want to look at that function that processes each item and adds it into the cumulative result. Any concerns about that? So fold left is automatically tail recursive, or even better, because it could be a while loop, right? Okay. So that in itself is not the concern. There is, in a way, a more basic concern, right? So the space complexity part we're supposed to be good on because of the fold left. There's a maybe more simple time complexity concern. Does anyone see that? So keep in mind that the fold starts with that Z argument, so in this case the empty list, and then for every item it finds, going through that list, X's, then it takes whatever we've built up so far, so that's R, and then it says R, and then attach F applied to the current X to the end of R. What's the complexity of that for a given R of, let's say, I items? Anyone? Yeah?
Isn't that
Right, exactly. So for an R of length I, you have to go from the beginning of R to the end, and then you append. So that is a problem here. So this is really only to illustrate that the fold is capable to achieve the map behavior, but it's not an efficient implementation of map for this reason. Just because even though the append, the plus, the colon plus looks symmetric to the plus colon, but the plus colon is just prepending at the beginning, and you're already pointing to the beginning, so that's an order 1 operation, whereas even though it looks as harmless as prepending, the colon plus means you got to traverse up to the end and then append the item, right? So that's harmless looking, but it's order n if the thing you're appending to is of length n. So that's why you should use that very cautiously, right? So it's basically not a good use of fold, but it illustrates that the fold is capable of achieving this behavior. All right. So what do we see now? Okay, also this fold is, this application of fold is one where the result type is not a scalar like in sum or max. Here it's actually a structure. Okay. So it's very general. The fold can do so many things. So basically most things that correspond to your typical iteration where you say, start with an initial value for each item, do something, and somehow modify that result value that you're building up. And then when you're through all the items, you got the final value, final result value, that type of thing. The fold will do this in a functional immutable way, and it will do it efficiently. It will do it as efficiently as it can, but what we're doing here, which is this colon plus for appending an item, that is something we're plugging into the fold. So the fold cannot improve on something it's given and has to do for each item. So that's why here the time complexity here, because for each step we're asking the fold to perform, we're doing an order n step. So the overall complexity of the map as fold is n squared, just so we're completely clear on this. All right, but we're really discussing this to understand the, let's say, the flexibility and power of the fold in terms of expressing all of these kinds of behaviors. So the fold generalizes this basically a common pattern, right? How would you have written any of these things recursively? So, for example, like this, if we had written, let's see, so the reverse is here, then the sum would look similar. So let's say def sum on list, x is list t. Okay, I gotta get that, whoops. Item type t. What does that produce? Well, a t, and what we do is, let's see if this works from a typing point of view. We might have to restrict it. So we'll say x is match, and then case nil, we get 0, and case head colon tail, we get h plus sum on list of tail, right? So here's the typing issue. So here we actually need this to be non-generic. So int Okay. So the fold left captures anything that has this kind of recursive pattern where for an empty list we return some initial result value, and for non-empty list we return some operations applied to the current item and recursively applying the function to the rest of the list, right? So you see how this sum on list follows the same recursive pattern as the reverse here, and the same recursive pattern even as the, let's see, the factorial. Actually, the naive factorial, you know, where we say case, even though that's not list-based, you know, but it's, you can think about it in a similar way, you know, where 0 corresponds to an empty list and non-zero corresponds to a list of that many nodes, so each node represents one more numerically. Okay. Let's see. So the direction I want to go into is the following. Okay. So the fold basically captures these kinds of recursion patterns. And if we wrote the map directly, you know, then let's do that. So let's do map on list, implementing this directly. So this is, of course, from T to U, and this gives us a list of U. And here it's the same thing. So what if we're looking at a nil? Well, then the result is also nil because we're preserving that structure. And if we're looking at a non-nil, then we're almost there. So this shows you that I'm manipulating the code I just wrote for the sum. What is missing? Well, we got to apply f to this h. Right? So that's all. F of h. So yes, it's not tail recursive, but it shows those same recursion patterns. And I forgot that argument, of course. We got to have the argument f from u from t to u. Okay. So here we go. And now we have a little issue. Yep. Does anyone see? Well, the plus is wrong. So let's try one more time. Okay. Because we're not doing a plus. We're doing the plus colon, or equivalently this, which I like because it matches what we have here to decompose it, and then here we're putting it back together in the same way we found it. So this shows you that it's structure preserving. Right, we're using the same thing to break up the current node of the list, and then to apply the f and put it back together. So I think that this third time should be the charm, well, almost the charm. Okay. Yeah. Okay, we got it now. So here, I forgot to pass the f. So now this should be it. Okay. Finally. Okay. So map on list. Okay. And now S map to S length. And then same thing here. Okay. So let's look at this and let's look at the sum on list again. I'm just going to bring this back up here because here, sum on list. So we can look at it next to each other. Here. All right. So you see that they follow the exact same recursion pattern, and that's what the fold is able to capture, but in an even more efficient way. Okay. So all of these are examples of fold. Any questions? So the next question, really the next step is, can we do this same kind of thing? So just the way we're kind of capturing, we're capturing a common recursion pattern across a lot of these different operations or behaviors, like here, the map, the sum, the reverse, all of those things. So that's quite striking that we can kind of separate the concern of the traversal, which is what the fold gives us, just this responsibility of traversing through the items in the list, and the more specific responsibility of taking a current item, a cumulative result so far, and then combining those two in some ways, which is what the second argument of the fold does. So that's where you customize it and where you get a map versus a sum versus a reverse, right? So that customization. So the next question I'm going to throw out here is really whether we could do something like that with recursion itself. How essential is recursion? Is this something that somehow we have to have, or is there a way to kind of factor out recursion similarly to the way we factored out these common recursion patterns that correspond to the fold? And it turns out that you can actually do this. So that's what we're seeing here, okay? Because you could kind of write a non-recursive version of the factorial we have at the top, right? So here's the straightforward factorial at the top on line 5. And we could write a non-recursive version of that if we say, well, let's take a function g of type int to int and produce a function of type int to int. So here we're taking the g corresponding to this int to int, and then we're taking the n corresponding to this int. So we're taking the g and we're producing this. And what we're producing has an argument n corresponding to this int argument type, and we're producing this. So if n less than or equal to 0, produce 1 or return 1, else return n times g of n minus 1. So the question is, how does that actually work? What does that actually do? Let's see. Yeah, so let's try that out. And start looking at it here. So it's actually going through these things, it's performing these assertions. But, let's try to play around with it a little bit. Okay. So what we have is this prefac, and if we invoke this on, let's say, the function from x to x, and number 3. Let's see what happens here. So that gives us a 6. What happened here? Well, let's look at the code. The code says, okay, so G is now int to int. I mean, x mapped to x, meaning the identity function. Okay. So then we gave it a number 3 as n, and it said, okay, that's greater than 0, so let's do 3 times g of n minus 1, so n minus 1 is 2, and g is just the identity function. So it gave us 3 times 2. Yeah, okay, fair enough. Not very useful so far. What if we say x mapped to 1 times 3, that gives us just a 3, okay. So what we can do then is, we can play around with it a little more. So here's the function that produces 1. So this is equivalent to saying function 1 or val 1 is x mapped to x, where x is of type int. So this 1, no matter what argument you give it, 5, it'll always give you 1. Okay? You give it 55, it'll say. But why is it useful? Well, because there are situations where we need something that takes an argument. That's what makes it different from the number 1 itself. Right? So we can pass it as an argument in situations where something needs an argument. Okay. And if we take this prefactorial and we pass 1 as g, so the 1 function, then this will be whatever n is, right? Because g, regardless of argument, in this case will give you 1, so this will always be just the argument itself. So prefac 1, function 1, applied to number 5 will give you 5. So let's play around with this a little more. What if we take the prefac 1 and stick it in here as the g? And we start with 5 as n. So n is 5, and then it says n times g of n minus 1, and that was the prefac of 1, which preserves its argument. So when that gets to 5, it gives you a 4. So that's the 4 that we get from here. Right? N is 5, and from here we get the 4. So what if we continue building a little chain here, just wrapping this prefac around it? What you're seeing is we're basically working our way toward the factorial. So in other words, if we apply prefac to itself enough times, then we effectively compute the factorial. Right? So what I'm trying to get to, there's a kind of loose correspondence to the prefac being the second argument of the fold, which says, what we're doing to the items to get the result. Right? So the missing piece is the equivalent of the fold. So we have the equivalent of the op for the fold. That's the prefac is an example of that. So if we apply that sufficiently many times to itself, we basically get back that recursive behavior. The missing piece is what's the more general recursion equivalent to the fold itself. Okay? So in other words, is there something to which we can just give the prefect. That will then give us the recursive factorial. Okay, so that's the idea. And it turns out that there is such a thing. Okay. Also, just you notice, if the chain is longer than necessary, it's still okay, you know, because at some point you reach that base case and you no longer try to go further along the chain. Okay. So what you could do is you could say, let's use recursion at the Scala level to say, okay, factorial is prefact applied to factorial. So it means like prefact basically applied to itself, because fact2 is prefact applied to itself. So it's like, see how the prefact takes that, has that first argument G. So if you kind of tie prefact into its first argument G, if you feed that back into it, then that's what gives you recursion. And you're seeing that here. So you're sticking the thing itself, because fact2 is defined to be prefact, and then applied to itself, that gives it back to you. And you see, if you apply that to 5, you know, this assertion passed when I just ran the code. Okay. So, there's other stuff that doesn't work, but that's just because of the initialization order of top-level Scala objects, so we don't need to worry about that. And then if you do it like this, you get a Stack Overflow error, so it catches those. So the right way, we have to have some kind of context because of the top-level initialization semantics. So anyway, that's just a short digression. The key point is, here we're using recursion again at the Scala level to kind of plug prefact into itself as its own first argument. And that means we have basically an infinite supply of elements in this chain that we need to handle recursion of arbitrary depth for an arbitrary integer argument to compute its factorial. The question is, can we write a function that's kind of like fold that will take a function such as prefact and make it a recursive version of itself? And that kind of thing is called a fixed point combinator. Fixed point means if you apply something to itself enough times, it'll stabilize at some point, and that's why you saw here, like, if you have a longer chain than necessary, it kind of stabilizes after it reaches the fixed point. So it doesn't matter if you do it more times past the point at which you reach that fixed point. And the fixed point, so-called fixed point combinator, generalizes recursion itself in a similar way that fold generalizes a certain common recursion pattern. So the fixed point combinator, we can actually define it in Scala. So it's called the Y combinator. So some of you might have seen this tech news site called the Y Combinator, but that's actually, so it's actually a venture capital firm called the Y Combinator, and they have like a technology news site, right? I'm sure many of you are aware of that, but they called it Y Combinator because of this Y Combinator, not the one I wrote here, but in general, the concept of the Y Combinator that's capable of kind of expressing recursion just as a function. And by applying that to a function from a type T to a type T, or rather from a type argument type to result, producing argument type to result, and it forms the fixed point, which is simply argument to result type. Right? So our prefact has this kind of type, where A and R happen to be the same. And if you apply the Y combinator to that, you get the actual factorial back. So here we were able to separate the concerns of what happens in each recursive step. And so that's what the prefact does. And then the separate, more general concern of saying, well, I want this recursion or these steps to occur as long as necessary for a given argument, meaning until the fixed point is reached. So provide a possibly unlimited or unbounded supply of recursive calls, and that's what the Y combinator does, because it says, all right, let's take our F, like the prefact, and just apply it to Y applied to F. So that's really how simple it is. And then we apply that to the argument. So this, the Y ensures an unlimited supply of recursive calls of F to itself. So, and in fact, if we do that, so Y of prefact behaves exactly like the factorial. So every time it goes to the recursive case, it just picks up one more recursive call option, so to speak, or capability, and then at some point it'll reach the base case. The thing is, you cannot write it as a finite chain, because if you write something like this on line 42, that's good enough only for argument 5, but if you wanted to compute factorial of 11, you would need 11 nested invocations of prefact. So any finite such chain of invocations is going to get to its limit if you choose an argument that requires more of those invocations. And the only way to make sure you have an unlimited supply of these invocations is by using the fixed point combinator Y. Also, read these comments, because they tell you there's just a step-by-step proof that Y of prefact 3 equals 3 factorial. And then one could use induction to say, in general, that Y applied to prefact applied to N equals N factorial. We just have to do a proof by induction on N. Okay. So what do we do here? So here I'm showing another example, right? Because the length method is like the sum and the max we saw, right? So if the list is empty, the length is 0. If the list is not empty, the length is 1 plus the length of the rest of the list, right? So that's exactly here. It follows the same pattern as those things we just looked at earlier. And in fact, if you apply the Y combinator to that, it'll also give you back the recursive version of length, right? So, how is let's say, how are pre-length and length related in the same way as prefact and fact? Just by, instead of having a direct recursive call to itself, we're calling another function, seemingly another function G, and the G has to come from somewhere, so we have to introduce that as an argument here, right? So the relationship between length and pre-length is the same as the relationship between prefact and the simple fact up here, where here we make a direct recursive call to this fact, and in prefact we replace that recursive call by a G, but then that G has to come from somewhere, and that somewhere is basically the argument here that we introduce here. So why are we doing this? Well, because we are okay, yeah, here's another one, like a trace function. So this shows that, you know, we can have a trace that takes an f, prints the argument, then performs f, and then prints the result. And that f could be an arbitrary function from argument to result type. And then we can use trace on tree length. So trace composed with, you know, this is mathematical composition of functions. And that's why here, you know, if I do this call trace for length, actually I wanted this. So we'll do the call trace here for length. You see how it prints the argument, then makes the recursive call, which means it prints the next argument in the recursive call chain, and then it gets to the base case in the middle of that trace, and then it backs up and prints the results. And then at the end prints the final result. So the trace we can compose also with a factorial. So in this case, we get the recursive calling chain as we're descending, and then we're coming back up with the result values. Okay? So the point of the trace is to show that there's actual value in opening up the recursion instead of writing factorial in such a way that it calls itself directly. If we open it up and say, well, it's called G, that opens it up and makes it possible to inject something like the trace. Because otherwise it's closed. But if we say, well, there's that argument G, normally we apply normally we make the recursion directly into G using Y, or writing it directly recursively. But by leaving that open, we say, well, that G could be actually some other function applied to the function that we want to have a recursive behavior of. So that's why, you know, we're able to say Y of trace composed with, you know, functional composition that you're, of course, familiar with, you know, which is F composed with G, which really means if you apply this to X, it's the same as F applied to G applied to X, right? So that's the function composition we have here. And you can see how when you leave things open, instead of hard coding the recursion, you can actually put things, you can take them apart and then put them back together in different ways, and that's what this illustrates. So the next step, any questions? This is going to take some time to digest, you know, but you have some time maybe over the next few days. The next step will be to do the equivalent of these kinds of things that we're doing here at the value level or function level. We have to do that at the type level, and then we get similar kinds of benefits at the type level, which will give us more aggressive code reuse, where we can basically have a single behavior that's like the fold, and we can take advantage of the ability to unify things like lists, trees, or other similar structures, and basically consider all of those as special cases of the same thing. So that's what we're going to start next week. So let's transition to the presentation on scheme. Are you going to connect in some way, or HDMI? The problem is the HDMI system here is closed, you know, so what kind of connector do you have?
It's only HDMI, I think.
Yeah, let's use Zoom then. So I'm going to launch that.